Now, the adjusted R squared you can see is the same as the multiple R squared. However, once we get into multiple predictors, this adjusted R squared will become different and it will be the value that we will report. When we start getting into where we're predicting BMI from maybe weight and height and red and HDL and all these different things that are possible that we could use to predict BMI, the multiple R squared becomes irrelevant. It's unimportant to us. The adjusted R squared is what we will report. Now, when we get down to the F statistic, we get into the model diagnostic. So the model diagnostic is quite redundant here because our model consists of only one predictor. So our model is that line right there. Not telling us anything different. Notice that the p-value is the same. Notice that the degrees of freedom are different because it's on the F distribution, not the T distribution. And the F test statistic, as it turns out, is nothing more than the 31.745 squared that we have as our t-value. So this t-value squared is our F statistic. And again, this is just redundant information in the simple linear regression case because we only have one predictor. Now, once we get multiple predictors, we'll be looking at these predictors individually, and then we'll refer to this line as the model diagnostic, which takes all of the set of predictors and makes a statement on the effectiveness of our model as a whole, not for each individual coefficient, each individual predictor. So that, my friends, gives us the entire output for the simple linear regression. Now, I would also probably want to run a correlation test, and I would want my X to go first. It doesn't have to, but I think it's a good idea to get in the habit of that. And I want my Y to go second, so I can run a core test. And this gives me the correlation between the weight and BMI. Again, in a simple linear regression case where our correlation is pairwise and we only have one predictor pairwise, gives us the same thing. Notice the test statistic is exactly the same. Notice the p-value is exactly the same. Notice the degrees of freedom, exactly the same. Now, our confidence interval is different because we have a confidence interval for R and not for weight, which I'll show you how to get in just a second. And this, of course, is R, our sample correlation coefficient. So there's a lot to, you may need to watch this video a couple times. There's a lot going on in this video because there's a lot of information that's provided in this output. Now, I talked about the difference in confidence interval. So if I do confidence interval for the model, what I'll do is I'll get my confidence interval for my intercept right here, my confidence interval for my predictor right there, and my confidence interval back here for the correlation coefficient. Those are three different confidence intervals, all kind of smack dab into one problem. So right now, before proceeding, it is extremely important that you can tell me what every single number in this output represents, that you can understand the difference between the correlation and the coefficient information, and that you can calculate the confidence intervals for our intercept and our predictor. Guess what happens when we have multiple predictors? BMI predicted by weight and height and LDL, for example. Let's say we have three predictors. Well, then you'll have confidence interval for all three predictors, weight, height, and whatever else I said. Okay, now it turns out over here, this is super easy to do, and I like the simplicity of this. After you get your data loaded into StatCrunch, just go to Regression Simple Linear. Select your X variable, and this is a little different. Over here, the Y variable goes first. Over here, the X variable goes first. You just have to remember those things. Have to tattoo them to the brain. So I want weight to predict BMI. Now, I want my hypothesis test first for the intercept and slope. And I want to get some stuff. Now, I'm not going to get into these things yet, but I'll tell you what, I'm not going to get into those at all. We'll get into that next video when we start looking at how to test assumptions and how to write things up and so on. So I think this will do it. So let's just go compute, and let's look at the difference. So up here we have this output. It says our dependent variables BMI, our independent variables weight. This gives us our model, which again I get from the 4.32 plus the 0.03, but it gives to you in a kind of a nice compact form. Tells you our sample size. Notice it gives us our correlation coefficient, which we got from this command, 0.878. Notice it gives us our R squared, 77.2%. Again, same thing we got right there, 77.2%. And it gives us our estimate of the error standard deviation that we get right here. So we get all the stuff the same over in StatCrunch. The next thing we get is our parameter estimates, which is the information we get out of our coefficient table right here. We get our estimate, we get our standard error, we get our degrees of freedom, we get our test statistic, and we get our level of significance of the p-value. Notice that all this information is the same over here as it was as we calculated in R. Now, one thing that's a little different is we have what's called an ANOVA table for regression. This information is given over here. It's just a little different form. This is the model diagnostic. Notice degree of freedom 1, 298. Notice degree of freedom 1, 298. Notice our F statistic is 1007.75. R has rounded that to 1008. And notice our p-value is statistically significant at the 0.001 level, which is the same p-value we have right here. It's just reported a little differently. Next, we actually get a scatter plot of our model. So I can do that over here. I can just do a plot of weight over BMI, and I can create what's called the AB line of the model. So the counterpart in R to what we get in StatCrunch is accomplished with this command. So you can see that eyeballing the tendency of the data tends to fit nicely a linear model. And I would feel, at least at this stage, I would feel very confident in making predictions of someone's BMI based on their weight from this model. So we can get an indication that, for example, for a weight of 120, if I come up to the line, the red line, and stop right there and then go directly over, then I would predict the BMI for a weight of 120 to be about 38, 39, something like that. 140, again, just try to go up as the best you can to the line. It's about right there. Okay, go over. It's about 45. Now, if we want a more precise measurement, we just put 120 in our model, and multiply by 0.301, and then whatever we get, add the intercept, and we can get our predicted value, just as we can do over here. All right, gang, it's all I got. I think this went on a little bit longer than, but there was a lot to accomplish in this video. Take care.